Imagine a silent wanderer drifting through the dark ocean of space. But this one was different. Its tail didn't stretch away from the sun, it reached toward it. Astronomers call it the anti-tail enigma of Three-Eye Atlas, a cosmic puzzle rewriting the rules of light and dust. And this video is based on the latest research of October 24, 2025. So while you relax, you'll also discover fresh, fascinating facts about our universe. What hidden forces could make a comet defy the very star that warms it? Let's drift together through the calm of interstellar space and uncover this mystery. And remember, just one subscribe gives me the motivation to bring you relaxing, science-filled journeys every single day.
Welcome. You are watching Whisper Science. Make sure to subscribe and join us for more amazing science content. Now, let's move back to the video.
A quiet night at the remote observatory in Chile. The dome opens. The sky's blackness spills across the lens, and the automated eyes of the survey telescope scan the firmament. It was here on the night of July 1, 2025, that the eyes of humanity first captured something not quite like the rest. A faint moving point of light, cataloged by the Asteroid Terrestrial Impact Last Alert System, ATLAS. From the raw metadata, an object at roughly magnitude 18 situated 3.5 AU from Earth and heading inward with a speed inconsistent with any standard solar orbit. The initial flag went up. Within 24 hours, orbit calculations revealed an astonishing truth. The trajectory was hyperbolic. This was not an object bound to the sun. It came from the stars beyond. In the days following the discovery, dozens of telescopes around the world pivoted to focus on the visitor. The notion of an interstellar interloper is rare. Only 2 had been confirmed before this moment. But here was another, the third of its kind. The vastness of space had gifted Earth a messenger. Once the orbit was computed, the designation came Three-Eye Atlas. 3 for the third interstellar object, I for interstellar, identified by the survey that found it. The data arrived in waves. Pre-discovery archival images, fleeting glimpses of a coma, evidence of outgassing faint but real. The Zwicky Transient Facility and other wide-field observatories unearthed frames, showing the object passing unnoticed among dense star fields weeks before formal recognition. These pre-covery detections revealed that the visitor was already active, even when many assumed it still lay dormant. Perhaps it carried within it frozen ices that began to sublimate far from the sun, an early sign that its origin was distinct from our own comets. By mid-July, the image sets sharpened. The Hubble Space Telescope captured the most detailed views yet, enabling size estimates of the nucleus, somewhere between roughly 0.32 kilometers and 5.6 kilometer across. The uncertainty vast, the implication clear. The object could be larger than many previously observed interstellar visitors. At the same time, its velocity stood out. Estimates placed its excess speed at tens of kilometers per second, above what could be accounted for by the sun's gravity alone. More energetic, more daring. For astronomers, the discovery phase was electric. Within laboratories and remote mountaintops, the hum of instruments and the click of shutter releases gave way to quiet reflection. What star system could have cast this fragment into the void? How long had it wandered? What secrets did it carry? The realization settled. This object did not arrive to linger. It would pass quickly, perhaps one of the briefest opportunities humanity would ever have to touch material born around another. Star-ground-based photometry showed the beginnings of a coma, a diffuse envelope of gas and dust, and Spectroscopic observations began to detect volatile releases. By late July, multi-wavelength teams were at work, measuring the composition of the emitted gases, the colors of the dust, and the structural geometry of the rapidly forming tail. Observers noted that the coma's redness increased over days, suggesting evolving surface conditions or dust enrichment, materials perhaps baked in a fiery crucible long ago in another system. In the silent spaces between each coordinate update and orbital calculation, astronomers realized they were bearing witness to an extraordinary encounter. Tens of thousands of years ago, or perhaps millions, the object had broken free from its host star's grip, ejected into the interstellar dark, traversing the galaxy before stumbling upon the reach of our sun. Now, here it was, accelerating toward perihelion, its destiny ordained. There was a hush in the control rooms when the meaning crystallized. This was not a moment for casual observation. It was a confrontation with the unknown. A cosmic fragment shaped by physics we mostly understand, yet arriving in a manner that invited other questions. As twilight deepened on observatory ridges, the scientists and their machines stood ready. The visitor had arrived at the edge of night, and with it the edge of our knowledge. And so the journey began. From discovery to documentation, from sight to speculation. The path of 3I Atlas promised to reveal not just what it is and where it came from, but also how the cosmos whispers to us, through travelers from afar, that our solar system is not an island, but a passageway. In the darkness of a Chilean night, the sensors flickered and registered a point of light. And with that, humanity's gaze widened. In late July 2025, when 3I Atlas crept deeper into the sun's domain, something began to stir in the images returning from observatories across the planet. At first, it was a barely perceptible asymmetry in the halo surrounding the nucleus, one subtle stroke of brightness extending toward the east, suspiciously close to the solar direction. Analysts dismissed it as noise, a calibration artifact, perhaps a passing background star bleeding into the frame. But night after night, the structure persisted, sharpening as the comet advanced. The anomaly had form. It had direction. The moment of confirmation came in the first week of August, when the European Southern Observatory's combined exposures revealed what could no longer be ignored. A luminous extension pointing not away from the sun, but directly toward it. The physics seemed reversed, as though some unseen hand had inverted the law that governs comets. In that instant, one of nature's simplest signatures, the way light pushes matter, appeared to falter. Across continents, observatories compared their data. Polarimetric reading showed a strange negative phase angle, suggesting that the dust grains in the sunward feature were larger and more reflective than those streaming away behind. Hubble's refined imagery traced a smooth arc connecting the nucleus to a tapering filament, glowing faintly against the black. Even JWST, operating far beyond Earth's atmosphere, caught spectral hints of carbon dioxide and metal-rich dust rising in that same improbable direction. For veteran comet scientists, the sensation was déjà vu. They recalled a handful of solar system comets that had, for brief hours, seemed to grow anti-tails, illusory structures formed by perspective. When Earth crossed the comet's orbital plane and looked edge-on through its dust sheet. In 1957, Arend Roland displayed such a ghostly finger reaching sunward. Hale-Bopp showed a faint mimicry in 1997. Yet those illusions depended on geometry, not defiance. The anti-tail of 3I Atlas was no trick of alignment. Even as Earth shifted its vantage point over the following weeks, the tendril stayed fixed toward the sun, brightening slightly with each passing day. The data threads converged into astonishment. According to radiation pressure calculations, particles of the size implied by the images should have been blown outward within hours. Solar photons exert a measurable push, tiny but inexorable on every grain of dust. To resist that push, to move against it, required forces unaccounted for in any standard model. Some speculated that the grains were far denser, perhaps metallic, their inertia overpowering the light's gentle shove. Others wondered whether electric or magnetic effects, induced by the solar wind's charged plasma, might be steering the particles sunward along invisible field lines. As debates filled the digital corridors of research networks, the comet itself offered no explanations. It continued on its inward journey, silent, indifferent to the turmoil it caused among those who studied it. Telescopes tracked the changing ratio of brightness between its conventional tail and its inverted one. The former obeyed expectations, fanning outward behind. The latter remained needle-thin, eerily stable, like a compass needle refusing to waver. Then came the color measurements. Spectrographs separated the sunlight reflected from the dust into wavelengths, revealing subtle hues. The normal tail gleamed a dusty amber, typical of silicates and carbonaceous compounds, but the sunward filament shone with a colder bluish tint, an optical signature consistent with fine metallic grains or ionized particles scattering shorter wavelengths. A portrait began to form. An object composed of material unlike that of our solar system, perhaps forged around a hotter, heavier star. In research centers from Maryland to Madrid, models multiplied. Magnetohydrodynamic simulations showed that under certain orientations, the Parker spiral magnetic field of the solar wind could, in theory, wrap around an incoming comet's coma and channel some charged particles backward. Yet those same models demanded densities and charge separations that bordered on implausible. Others turned to grain size distribution. If the smallest particles were expelled rapidly while heavier fragments clung close to the nucleus, then under the right viewing conditions the remaining stream could appear to point inward. But such conditions required delicate timing and unlikely coincidence. Amid the arguments, a quieter insight surfaced. Perhaps what they were witnessing was not defiance but dialogue, the way alien dust converses with familiar sunlight. The laws of physics had not reversed. Rather, new participants had entered the stage, bringing with them properties that bent those laws into unexpected shapes. Each night, as data flowed in, the story deepened. The sunward plume fluctuated, at times pulsing brighter as if breathing with the solar wind. Its structure seemed alive, responsive to invisible rhythms in the heliospheric environment. And behind the measurements lingered a feeling that many scientists were reluctant to voice, awe tinged with unease. For every mystery uncovered, there lies the possibility that our understanding is provisional, that nature keeps a few of its axioms loose, waiting for the next traveler to redraw them. By early September, the world's leading observatories had joined forces in coordinated observation campaigns. In shared databases, terabytes of imagery accumulated: infrared, optical, ultraviolet, polarized light, time-resolved photometry. Algorithms traced the shifting dynamics of the dust flow. Plasma physicists mapped magnetic models across the comet's trajectory. Slowly, patterns emerged, a suggestion that the so-called reversal was more than a single feature. It might represent a complex superposition of material streams, an evolving sculpture carved by radiation, gas pressure, and magnetism all at once. Still, the human mind is drawn to symbols. The sight of a comet's tail reaching toward the sun carried a poetry too profound to ignore. In ancient times, comets were omens, messengers from the gods. Now, in the precision age of data and spectroscopy, the message came coded in vectors and photons, but its emotional weight remained. Something foreign had entered the solar cathedral and bent its light backward. As September drew to a close, 3I Atlas moved past perihelion. The sun, blazing behind it, should have driven every particle outward, stripping the coma bare. Instead, the tendril persisted a little longer, thinning gradually like the last ember of a paradox refusing to extinguish. When finally it faded from detection, the debate did not. Within observatory logs and archived frames, the anomaly endured, a snapshot of the moment when light appeared to lose its certainty. The discovery of the anti-tail marked the first real fracture in the comfort of prediction. It reminded scientists that even well-worn laws might show new faces under unfamiliar conditions. Somewhere between particle dynamics and cosmic metaphor, the visitor had traced a single question across the void. If sunlight can sometimes draw matter inward, what else in this universe might we have misunderstood? And so, with the first glimpse of reversal, 3I Atlas ceased to be merely another interstellar wanderer. It became a mirror, reflecting not just the light of a distant star but the assumptions of those who believed they already knew how light should behave. Long before humankind named them, comets were the universe's drifters, fragments of ice and dust sculpted in the cold shadows beyond the planets. Their lives are defined by heat and exile. For millennia they travel frozen and inert through the dark, until the distant glimmer of a star stirs their slumber. When sunlight reaches them, molecules awaken. Ice's sublime gases burst forth and the sleeping rock becomes a living apparition. The transformation is violent, radiant, and governed by rules so consistent that astronomers once believed they had decoded the script of every comet that would ever pass this way. Those rules begin with the sun itself. Every comet's form is a dialogue between heat and pressure, between radiation and escape. As photons strike the nucleus, energy transfers to the surface, dislodging molecules of carbon dioxide, methane, water, ammonia. They surge outward, dragging fine dust along. Solar radiation and the solar wind, streams of high-energy particles, impose direction. Together they sculpt the twin identities of a comet's tail. The ion tail, straight and bluish, made of charged gases swept directly away by the solar wind, and the dust tail, curved and golden, shaped by the slower, subtler push of sunlight itself. The physical reasoning behind this choreography is elegant. Radiation pressure acts inversely to the square of distance, pushing dust away along vectors nearly opposite the sun. In laboratory analogs, micron-sized grains respond predictably. Light pushes them outward, a slow acceleration that creates a graceful arc through space. Every comet we have ever studied, from Halley to Hale-Bopp to Borisov, obeyed this solar choreography. No exceptions, until 3 Atlas. When the interstellar wanderer began to glow, astronomers expected the same geometry. Yet data soon revealed a system whose anatomy contradicted the textbooks. The primary tail behaved as expected, fanning outward in the anti-solar direction. But layered atop it was a secondary plume, thin, persistent, luminous, stretching toward the source of light itself. It was as though gravity and radiation had exchanged roles. The more closely scientists examined the data, the more impossible the picture became. To unravel the paradox, they dissected the physics grain by grain. In the coma, dust particles range from fractions of a micron to pebbles several millimeters wide. Their motion is influenced by four principal forces: solar gravity, solar radiation pressure, gas drag from sublimating ices, and electromagnetic coupling with the solar wind. On Earth, these principles translate cleanly into equations. In deep space, however, they dance with variables of charge, spin, density, and time delay. A single difference in material composition can invert the choreography entirely. WST's infrared spectrum provided the first clue. The gas surrounding 3I Atlas contained far more carbon dioxide than water, an inversion of the usual order. On Earth, CO₂ freezes at much lower temperatures than water, which means this comet's volatile reservoir was forged in an environment far colder than the solar system's birthplaces. Moreover, embedded in that ice were fine metallic particles, nickel, cobalt, chromium, atoms that require high stellar temperatures to form. Such a mixture hints at violent origins. Perhaps a planetesimal torn apart near a dying star and then ejected into interstellar exile. Those metallic inclusions altered the behavior of the dust. Unlike ordinary silicates, these grains could carry significant magnetic charge. Magnetism, that subtle, invisible hand. Within the solar wind flows the Parker spiral, a vast rotating field spiraling outward from the sun. To charged grains, it is not simply a breeze. It is a current, a map of paths unseen. If the dust of 3I Atlas was magnetically sensitive, it might not respond to light alone but also to those winding lines of force. Some simulations suggested that when the solar wind meets an electrically active coma, magnetic draping occurs. The field bends around the object like silk around a stone. In that sheath, charged particles could be deflected sunward, tracing luminous filaments that mimic a reversed tail. And yet, magnetism alone could not explain the full geometry. Researchers turned to rotational dynamics. Every comet spins, some slowly, some rapidly. Jets of sublimating gas act like miniature thrusters, altering spin and torque. If the axis of rotation on 3I Atlas was tilted toward the sun, outgassing from a specific hemisphere could project material along that very line. Over hours, the jet might carve a narrow plume oriented sunward, while the broader tail streamed behind. Such jets are common, but for their alignment to create a persistent anti-tail required exquisite balance, one that nature rarely maintains by chance. As models multiplied, so did metaphors. Scientists spoke of breathing comets, magnetic tethers, optical illusions cast in plasma. Beneath the language of equations ran a current of wonder, that a single visitor could expose how fragile our understanding remains. Atlas had become an anatomical puzzle, a being whose organs refused to align, whose circulatory system pulsed in two directions at once. To comprehend its anatomy, one must imagine the forces at play as threads of tension crossing an invisible sculpture. Photons push outward, gravity pulls inward. Gas jets twist sideways. Magnetic fields swirl around. The comet's structure is not a simple tale but a living field of competing intentions. A storm of microscopic motions whose sum paints an elegant, baffling shape in the void. For those watching from Earth, the spectacle carried both scientific urgency and quiet poetry. In that slender line pointing back toward the sun lay a reflection of cosmic contradiction. Cold matter drawn toward heat, shadow reaching for light. The equations remained faithful to their logic, but the narrative felt mythic, as though the universe had decided, for a brief moment, to sign its name backward. As September unfolded, the comet's anatomy changed again. The sunward filament thickened, then thinned, responding to fluctuations in the solar wind recorded by spacecraft nearer the sun. Its behavior seemed coupled to the star's moods, trembling when magnetic turbulence intensified, calming as conditions smoothed. This synchrony hinted at real physical correspondence, the tail as an instrument playing to the sun's magnetic symphony. In conference halls and online discussions, the term anti-solar dynamics gained traction. No longer merely a curiosity, 3I Atlas became a testbed for how interstellar matter interacts with our heliosphere. Its anatomy was a cross-section not only of the comet itself, but of the invisible ocean through which the sun sails. Studying it meant studying the boundaries of our cosmic weather. When the object eventually passed its closest approach, telescopes recorded a final haunting portrait. Two luminous strands extending in opposite directions, balanced like the arms of a cosmic scale. In that symmetry, one tail fleeing, one reaching, lay the story of forces in conversation rather than conflict. The anatomy of 3I Atlas revealed that even in the apparent defiance of light, there is no rebellion, only the universe rehearsing its complexity in full view. The visitor would continue outward soon after, fading into the outer darkness, leaving behind nothing but equations, imagery, and a renewed humility. Its anatomy, once alien, now stood as a reminder. Every comet is a vessel of contradictions, and every rule in nature carries the seed of its own exception. In the wake of 3I Atlas, the word comet seemed insufficient. What drifted across our sky that season was something else entirely. A dialogue between stars, a sculpture of plasma and dust spelling for those who could read it, a single, fragile truth. That even the simplest motions in the universe are written in a language we are still learning to speak. For a brief season in the middle of 2025, the quiet rhythm of observatories across the planet broke into coordinated urgency. The moment the strange geometry of 3I Atlas became undeniable, every major astronomical facility in the world seemed to turn its mirrors and sensors toward the same target. The faint intruder from interstellar space had provoked what scientists later called the fastest global convergence of telescope time in history. On mountaintops from Chile to the Canary Islands, at stations in Hawaii, Japan, and South Africa, domes opened in synchrony beneath the rolling line of night. The object was faint, barely bright enough to paint a trace on long exposures, but its behavior demanded precision. Every photon carried a hint of an answer, and perhaps a new question. Within days, data began to pour through international networks. Images streamed from Hubble's optical arrays, spectra from JWST's infrared sensors, radio echoes from ALMA, and polarimetric patterns from La Silla and Paranal. Scientists who had never before shared a project suddenly found themselves in a joint experiment conducted at the scale of the solar system. It was the anti-tail that unified them, a sunward streak of light that refused to disappear, defying radiative logic. Measurements confirmed that it was not a transient jet, nor a trick of Earth's perspective. It was physical, dynamic, measurable. The more instruments observed it, the more pronounced it appeared. In September, Hubble captured a time-lapse sequence that showed the tendril thickening even as the main tail thinned, an inversion of expected evolution. In laboratories and university offices, researchers struggled to contain their fascination. The simplest of forces, sunlight, seemed to have changed its mind. Radiation that should push was now aligned with motion that pulled. For some, it felt as though nature itself had turned its face slightly, revealing a side not previously seen. International collaborations formed overnight. NASA and ESA established a joint task group under their planetary science divisions to coordinate spectral analysis. The Harvard-Smithsonian Center for Astrophysics assembled its global mailing list of cometary experts. Over 200 scientists contributed observations, models, and simulations within a week. Even amateurs joined in, feeding backyard telescope data into public archives. It was a collective pursuit, a scientific symphony responding to an alien note. The more the world looked, the stranger the picture became. JWST's spectrometers identified volatile outgassing dominated by carbon dioxide rather than water, and emission lines of nickel, a rare find in any cometary spectrum. Nickel-rich dust grains are heavier, denser, more reflective. When aligned within magnetic fields, they behave differently under radiation pressure, sometimes scattering photons in ways that can momentarily simulate attraction. Yet even with these explanations, the degree of alignment required seemed implausible. The equations worked only on the knife edge between probability and miracle. Simultaneously, ESA's solar orbiter, stationed within the inner heliosphere, detected a sudden distortion in the solar wind's magnetic pattern, a ripple sweeping through the heliospheric current sheet at the very time 3 Atlas's sunward plume reached maximum brightness. Correlation did not imply causation, yet the synchrony was haunting. In a matter of hours, global chatter filled research networks. Could the visitor have acted as a tracer, revealing invisible waves that constantly pass unnoticed through the sun's domain? The emotional atmosphere of the scientific community oscillated between awe and disbelief. Astrophysicists accustomed to measured caution began to describe the event with words like impossible and transformative. Plasma physicists proposed complex coupling mechanisms. Photometric experts questioned the calibration of instruments. Chemists modeled ice sublimation at interstellar densities. Each discipline found itself brushing against the limits of its language. Outside the research circles, the public caught wind of the mystery. Images leaked online, the comet's faint outline, one tail streaming outward like a normal traveler, the other a pale finger of light pointing homeward to the sun. In those images, people found metaphor, hope, contradiction, beauty. The visitor became a symbol of defiance, a silent pilgrim drawn back to the star it should escape. Meanwhile, inside data archives, silence prevailed. The numbers themselves, spoken whispers, column densities, velocity dispersions, albedo ratios. In the sterile rows of figures lay something profound, the record of nature behaving beyond precedent. As analysts parsed the variables, they discovered subtle oscillations in brightness that matched the sun's rotational period. Somehow, the anti-tail flickered in rhythm with the star's magnetic heartbeat. Then came the announcement from the European Space Agency's headquarters in Paris. Coordinated observations confirmed that the sunward feature extended for more than 800,000 kilometers, nearly twice the Earth-Moon distance. It was not a jet, not a fluke of perspective. It was a structure large enough to thread across the inner solar system, born of dust from another star. The revelation created a rare moment of unity across institutions normally separated by funding and pride. For once, every data stream converged on wonder itself. The Sunward Tendril, as it was now formally labeled in technical bulletins, had rewritten what a comet could be. At NASA's Goddard Space Flight Center, late-night meetings stretched into dawn. On projection screens, the heliosphere unfolded like a living map. Solar wind velocities, plasma densities, interplanetary magnetic lines curling and shifting. Somewhere within that great invisible sea, a filament of dust from beyond the stars was tracing unseen currents. To some, it was as though the universe had handed humanity a brushstroke on its own canvas. And beyond the laboratories, far from computers and equations, lay the emotional realization. This was the first time humankind had watched a material visitor from another system not simply reflect sunlight, but appear to respond to it. The cosmos for a moment seemed conversational. As October approached, the urgency began to soften into reflection. The comet was receding, its light fading from naked sensors. Yet the aftermath lingered. Universities prepared papers, observatories archived terabytes of imagery, and theorists continued to refine their simulations. The anti-tail, ephemeral in the sky, had left a permanent scar across the certainty of physics. In time, future missions would revisit the data, replot the parameters, adjust the assumptions. But the memory of that global shockwave, the collective gasp of humanity's instruments, would endure. Phi Atlas had turned every mirror on Earth toward itself. And in that reflection, science glimpsed both its fragility and its strength, the willingness to be astonished. For in the end, the shock was not merely scientific. It was existential. Light, long considered the simplest of truths, had shown that even it could mislead the eye. And as the comet slipped beyond detection, fading into the cold between planets, the question it left behind echoed across observatories. If sunlight itself can appear to draw matter inward, what else in the deep mechanics of the cosmos might yet be reversed? The deeper the world peered into 3i Atlas, the more the universe seemed to stare back. Each new image refined the impossible. A comet with a double soul, one tail fleeing the light, another reaching into it. At first, the anomaly looked like a misalignment, a trivial imperfection of measurement. But as data from every major observatory coalesced, the pattern held steady. The sunward filament was no mirage of geometry. It was a physical, measurable phenomenon evolving in step with the sun's own moods. To explain it, astronomers dismantled the physics piece by piece. They began with the framework of classical cometary motion, solar gravity, radiation pressure, gas drag, and electromagnetic coupling. In the familiar world of solar system comets, these four forces compose a perfect equilibrium. For 3i Atlas, that equilibrium shattered. Simulations run in the days after the Global Coordination meeting revealed an intricate interplay between gas jets and magnetized dust. The nucleus, slightly elongated, spun with a period of about 8.7 hours. Each rotation exposed vents that exhaled CO2 gas in brief bursts, driving plumes of metallic dust into the surrounding coma. Under normal conditions, the sunlight's push would scatter these grains outward. But this time, the surrounding solar wind was different. ESA's solar orbiter recorded a magnetic sector crossing, a region where the sun's magnetic field reverses polarity just as the comet entered its most active phase. In that moment, the solar wind became a storm of tangled fields draping around the comet's ionized atmosphere like fabric twisting in a current. When a charged dust grain entered that chaos, its motion ceased to obey simple light pressure. Instead, it was shepherded along curling magnetic lines that arced sunward before looping back outward. The result? A visible tendril tracing an invisible field. At NASA's plasma simulation labs, researchers built digital twins of 3I Atlas. On high-performance clusters, millions of dust grains swirled through virtual sunlight. When the simulated magnetic polarity flipped, a narrow filament formed precisely as telescopes observed. It was an extraordinary coincidence of timing. An interstellar comet intersecting a solar magnetic reversal, its charged dust briefly compelled to dance backward toward the star. But physics rarely gifts us with single explanations. Parallel analyses by European and Japanese teams uncovered a second mechanism acting in concert. The dust grains, heavy with nickel and cobalt, exhibited extraordinary reflectivity. Photons striking their surfaces did not merely impart momentum. They induced a torque. Instead of being pushed straight outward, the grains spun, twisting in the solar wind like tiny propellers. The combination of spin and magnetic charge caused some to spiral inward before dispersing, a microscopic ballet giving macroscopic shape to the anti-tail. For weeks, competing models filled the preprint servers: charged grain draping, rotational jet feedback, mass sorting illusion. None could capture every nuance. Some required the grains to be too large, others demanded unrealistic field strengths. Yet the convergence of evidence suggested a truth both simple and sublime. 3I Atlas's paradox was not a violation of law, but an intricate collaboration of them. Light, magnetism, and motion conspired to paint a form that no one had seen before. At a closed symposium held mid-October, 43 researchers assembled virtually to confront the paradox. Their screens glowed with simulations, each a tiny cosmos of dust and wind. When the heliospheric current sheet pulsed through one model, the filament brightened in perfect synchrony with real observations. The room fell silent. For a heartbeat, the mystery felt tangible, graspable. Then, as quickly, it dissolved back into questions. Outside the realm of equations, the implications rippled outward. If a single interstellar object could reveal the contours of our sun's magnetic architecture, what might dozens show? Could such visitors serve as natural probes, tracing the invisible scaffolding that encases the solar system? The thought electrified heliophysicists. 3I Atlas might be more than a curiosity. It might be the first messenger to make the unseen visible. Meanwhile, attention turned to the comet's chemistry. Spectroscopy confirmed a composition both ancient and alien, ratios of volatile ices unseen in any local comet. Embedded metals hinted at formation near a hotter, older star, perhaps within a binary system where stellar winds mixed elements at extreme temperatures. The paradox then began not at the sun, but at the comet's birth. Its dust, forged under alien conditions, carried intrinsic magnetic signatures. When these ancient grains entered our heliosphere, they resonated like tuning forks struck by a new magnetic field. In that resonance lay the poetry of science, two stellar systems conversing across light years, their materials briefly harmonizing in plasma and light. Back on Earth, computers translated this celestial dialogue into imagery. Data from JWST and Hubble merged into color-coded maps. Reds for carbon dioxide emission, blues for metallic reflection, greens for ion fluorescence. When the maps were overlaid, the anti-tail glowed brightest at the intersection of all three. It was the point where chemistry met magnetism, where the ancient dust of another world sang in the sun's wind. Still, uncertainty reigned. Every model left residuals, tiny mismatches between theory and observation. For scientists, those residuals are the pulse of discovery. In their gaps live new physics. The Sunward Tendril, as it was formally catalogued, refused to submit entirely to any explanation, as though it understood the value of remaining unsolved. By late October, as 3I Atlas drifted outward again, its paradox began to fade into the solar glare. Yet within its brief passage, it had exposed an unseen dimension of the heliosphere, the delicate boundary where radiation meets magnetism, where matter from other stars tests the fidelity of our equations. In the end, to dissect the paradox was to dissect certainty itself. What appeared as rebellion was, in truth, a revelation that even light and dust, those most obedient of cosmic citizens, can improvise when their origins differ. 3I Atlas had not broken physics. It had reminded us that physics is larger than the rules we remember. And so as the comet dimmed and the observatories closed their domes, a quiet humility settled over the scientific world. The paradox was not an error to correct, but an invitation to look again, to question deeper, to see in every deviation not defiance, but design. The sun is not silent, it breathes. A ceaseless exhalation of charged particles flows from its surface, stretching outward in all directions. A wind of plasma and magnetism so vast that it fills the solar system and defines its edge. This invisible storm, called the solar wind, carries the sun's magnetic field in great spiraling arms, wrapping the planets in unseen filaments of force. For decades, its pattern was known only by inference, measured indirectly by spacecraft that felt its gusts as they passed. But in the summer of 2025, the universe offered a map, drawn not by human technology, but by dust from another star. When 3I Atlas entered the inner heliosphere, it passed through one of the most intricate magnetic structures in the sun's realm, the heliospheric current sheet, a wavering membrane separating opposite magnetic polarities. This sheet undulates like a cosmic ribbon, rippling outward with each rotation of the sun. It is the place where the solar wind's opposing streams meet and braid, where turbulence and reconnection flare like silent lightning. Data from Solar Orbiter and Parker Solar Probe revealed that during the comet's passage, the current sheet was unusually active. Waves of fluctuating magnetism swept outward, and for a brief window those waves met an alien traveler. The charged dust surrounding 3I Atlas did not ignore them. It responded, aligning, twisting, tracing lines that human eyes could finally see in reflected sunlight. The mysterious sunward tail became a luminous contour of the solar wind itself, a filament sketching the invisible architecture of our star's magnetic field. In the combined images from Hubble and JWST, astronomers found subtle pulsations, brightening and dimming in cadence with magnetic oscillations detected by Solar Orbiter, 100 million kilometers closer to the Sun. The correlation was unmistakable. For the first time, scientists were watching the solar wind being drawn. Every fluctuation in brightness marked the passage of a wave through the heliosphere's tangled fabric. It was as though the sun's breath had found a pen. The revelation redefined what the anti-tail meant. It was no longer simply an anomaly of cometary physics. It was a diagnostic instrument. A natural probe had wandered into the perfect corridor, and its dust, foreign, metallic, magnetically responsive, had responded as if it were made for this purpose. By tracing the tendril's shape, researchers could map field lines in 3 dimensions, revealing curvature and tension that no probe had ever charted. This was something spacecraft could never achieve directly. The heliosphere is immense, its magnetic surface is shifting with solar rotation. Human instruments record only single points. They feel, but they do not draw. Through Atlas, by contrast, painted the structure with motion. Its path through the current sheet created a streak hundreds of thousands of kilometers long, a moving cross-section of space weather. In late September, magnetograms from Parker Solar Probe confirmed a reversal in field orientation, precisely as the anti-tail's direction pivoted slightly. The alignment was not coincidence. The comet had drifted across the fold of the current sheet, and its dust had obeyed the new geometry instantly, like iron filings rearranging around an unseen magnet. For a few days, humanity witnessed the solar wind made visible. To comprehend what this meant, scientists returned to history. For centuries, the sun's influence had been inferred through auroras, radio noise, and the whisper of cosmic rays. Now, with one interstellar fragment, the invisible had become visible. 3i Atlas had turned the heliosphere itself into a canvas. The collaboration deepened. Teams in Europe and the United States combined heliophysical data with optical measurements, reconstructing a volumetric model of the space between the comet and the sun. Supercomputers rendered the field in motion, vast curling arcs of magnetism, bright dust flowing along them like tracer dye through an unseen ocean. The resulting visualization stunned even veteran physicists. The anti-tail shimmered along one precise corridor of the heliospheric current sheet, revealing how magnetic flux ropes twist and converge before dispersing. This was the first natural 3D portrait of our sun's magnetic anatomy. But behind the triumph lay a whisper of unease. If a single interstellar object could unveil such structures, what else might it reveal? Structures we had never imagined. Did the heliosphere possess subtleties still hidden? Layers of current and turbulence waiting for other visitors to outline them? Among the scientists, there was a shared sense of reverence. They were witnessing not merely a comet, but a rare alignment of 2 cosmic rhythms, the solar wind's pulse and an interstellar wanderer's trajectory. That intersection had produced a phenomenon both artistic and diagnostic, a bridge between the physics of stars and the chemistry of dust. In conference rooms, researchers displayed the synchronized datasets like symphonies written in numbers. One line showing solar magnetic intensity, another, the brightness curve of the anti-tail. Peaks matched peaks, valleys mirrored valleys. It was as if the sun and the comet were performing a duet across millions of kilometers. By mid-October, 3i Atlas began to recede. The filament that had glowed so stubbornly faded, dissolving into the ambient haze of space. But the information it left behind was priceless. The heliospheric model derived from its passage now serves as a reference, used to refine predictions of solar storms and the boundary conditions of interstellar space. In a single encounter, a visitor from another star had improved humanity's map of its own. The poetic irony did not escape those who studied it. For centuries, comets were thought to bring omens, to trace fates written in the sky. Now one truly had, not prophecy but pattern. In its delicate sunward glow lay the handwriting of the solar wind, inscribed by dust older than the sun itself. In that realization came a quiet humility. The heliosphere, once imagined as a static bubble of influence, revealed itself as a living tide, its breath visible only when foreign dust drifted through. Without 3i Atlas, it would have remained unseen. With it, The sun's secret map had been sketched across the void, a transient drawing that lingered only long enough for humankind to notice before the wind erased it again. And so the maps of textbooks expanded. Between the mathematical lines of Parker spiral equations, new curves appeared, hand-drawn by an interstellar traveler. 3i Atlas had shown that the universe does not always require our instruments to reveal itself. Sometimes it simply sends a messenger to trace what has always been there, invisible, waiting for light from another world to show us its shape. As the sunward filament of 3i Atlas faded into the dark, the theories it left behind began to multiply like echoes. No single explanation could hold the mystery entirely, and so the scientific imagination scattered outward, each hypothesis a light searching through the fog. The first frontier was geometry, the oldest comfort. Perhaps some argued the anti-tail was nothing but perspective. Earth's orbit might have crossed the comet's orbital plane, making the dust sheet appear to lean toward the sun. But the numbers resisted this solace. The alignment was wrong, the geometry uncompromising. Even as the Earth moved along its orbit, the tail refused to shift. The illusion would not dissolve. Geometry had no answer. Then came the physicists of light. They spoke of scattering angles and albedo laws, of how nickel-coated dust grains could refract sunlight inward instead of outward under rare conditions. Light, they reminded everyone, is not always a simple arrow. It can twist when it meets a symmetry. In the labs of Berlin and Pasadena, plasma chambers recreated micro-worlds of charged dust, irradiated with high-intensity beams. For a moment, some grains did appear to drift sunward, pulled not by gravity but by radiative torque. The phenomenon was real, but faint, fleeting, and fragile. It explained part of the story, but not its endurance. Others turned to magnetism. The sun's magnetic field, coiled into the grand spiral of Parker's design, wraps around the solar system like invisible silk. If the dust of 3i Atlas was metallic and charged, perhaps those lines of force had reached out and shaped it. Simulations from the Max Planck Institute traced such magnetic draping with eerie precision. A sheet of plasma folding around the comet, pulling dust inward before releasing it again. To many, this model felt close, plausible, elegant. But even it could not explain the rhythmic pulses observed in the anti-tail's brightness, pulses that followed no solar period known. A third camp reached further into the chemistry of alien worlds. The metallic ratios in 3i Atlas, rich in nickel and cobalt, poor in silicates, suggested a violent birth. Some imagined a binary star system, one star dying, the other tearing away fragments from its companion's disk. The expelled debris, magnetized by the dying star's final outbursts, could have drifted across interstellar space, still carrying faint remnant fields. When such grains met the sun's own magnetism, they might not repel but align, like compass needles meeting a stronger magnet. In that meeting, the anti-tail could emerge not as an illusion, but as the last whisper of a long-extinct world. From these seeds grew wilder speculations. Plasma cosmologists proposed that 3i Atlas was coated in exotic ions from the interstellar medium, responding to electrostatic forces unfamiliar to solar system science. A few theorists invoked the concept of dark plasma, a hypothetical medium of weakly interacting particles that might occasionally influence ordinary matter through transient charge exchange. If such particles exist, they could subtly modify radiation pressure near magnetic boundaries, bending dust streams sunward. The hypothesis was fragile, almost philosophical, but it carried a seduction. The idea that this small comet might be the first tangible probe of a hidden component of the universe. Verification needed. Across conferences, discussions expanded beyond immediate mechanisms. Einstein's relativity had shown how gravity bends light. 3I Atlas now suggested that light itself might, in turn, bend matter through intricate feedback between reflection, spin, and field. The ghost of Hannes Alfvén hovered over the equations. His long-dismissed visions of cosmic plasma currents suddenly revisited. Hawking's old caution, that every anomaly is an invitation, not a contradiction, echoed through seminar rooms. One evening, as the working group at Goddard compared simulations, an image appeared on a monitor, a visualization of field lines colored by dust density. At its center, the comet's nucleus shimmered like a pale seed. From it extended two symmetrical plumes, one outward, one inward, balanced as if hung on a cosmic thread. The room fell still. Theories could fight over causes, but here was the aesthetic truth of it. The anti-tail was not chaos. It was geometry of a higher order, a new pattern written in plasma and light. Speculative voices went further. What if the anti-tail was an information structure, an emergent behavior of physics itself, a self-organizing system that momentarily carved order from randomness? In that view, the comet was merely the catalyst, the heliosphere the stage. For a brief moment, energy, charge, and motion aligned to create a transient shape of impossible beauty, like a snowflake forming and melting in a thunderstorm. Nature, indifferent yet expressive, had drawn an equation too complex for immediate comprehension. Even within the caution of scientific prose, awe found its way. Papers described anomalous coherence, plasma coupling harmonics, magnetic self-symmetry. The words reached for poetry because the phenomenon itself demanded it. For 3I Atlas was not just an interstellar stone, it was a demonstration that the universe still surprises, that between the equations there is room for wonder. In the months that followed, the theories settled into layers, the pragmatic, the speculative, and the philosophical. The pragmatic saw the anti-tail as a blend of magnetic draping and heavy grain dynamics. The speculative envisioned unknown interactions at the heliospheric boundary. The philosophical asked what it meant that an object from another system could so elegantly reveal the hidden architecture of our own. Late in October, when the comet had faded beyond the reach of even Hubble, one final synthesis emerged. The anti-tail, scientists proposed, was an intersection, a coincidence of timing between an interstellar traveler and the living weather of a star. It was both messenger and mirror. Messenger because it carried the dust of another world. Mirror because in reflecting the sun's light backward, it showed humanity its own curiosity bending toward the source. By then, the debate had softened into contemplation. 3I Atlas had proven that a single anomaly could reopen entire disciplines. Theories would continue to multiply, refined with each new visitor that crossed the solar frontier. Yet all who had watched agreed on one quiet truth. The universe does not contradict itself. It reveals itself slowly, in riddles written across the night. And so the chapter of explanations closed, not with certainty but with gratitude. The anti-tail remained in data and in memory, a delicate symbol of inversion, a reminder that even the simplest forces, when cast through alien matter, can compose symphonies we have not yet learned to hear. When 3I Atlas finally slipped into the sun's distant haze, humanity was left with a puzzle and a calling. The faint streak that had pointed toward the sun faded from view. but the questions it awakened refused to vanish. The scientists who had watched it depart did not lower their telescopes. They began to build new ones. Across continents, a quiet renaissance stirred in the engineering bays of observatories and laboratories. What had been a sudden convergence of curiosity during the comet's brief passage was becoming a long campaign, a determination to be ready the next time an interstellar wanderer appeared. Because another will come, the galaxy, it seemed, sends such messengers regularly, perhaps one every decade, and the lesson of 3i Atlas was clear. We must learn to listen faster. At NASA's Jet Propulsion Laboratory, programmers refined the alert networks that link sky surveys into a single heartbeat. The Atlas telescopes that first spotted the visitor in July 2025 now share data in real time with the Vera Rubin Observatory in Chile. Algorithms trained on the signature of that faint, hyperbolic path learn to recognize its kin, objects whose speeds betray their foreign birth. The aim is to spot the next one within hours, not days, so that every eye in orbit and on the ground can awaken before it fades. New missions have taken form in that urgency. ESA's Comet Interceptor, a spacecraft designed to wait patiently at the L2 point, will one day spring into motion when the next interstellar object is found. Its trio of probes, each carrying imagers, spectrometers, and plasma analyzers, will scatter like seeds, intercepting the target from multiple angles. What 3i Atlas revealed remotely, Comet Interceptor hopes to touch: the texture of alien dust, the chemistry of ancient ices, the whispers of magnetic memory locked within grains older than the sun. Elsewhere, heliophysicists refine the tools that sense the invisible. The Parker Solar Probe and Solar Orbiter continue to dive through the furnace of the sun's wind, mapping magnetic flux lines that once tangled around 3i Atlas. Their data feed into the coming IMAP mission, which will listen from farther out, where the solar breeze meets the breath of interstellar space. Together, these machines weave a three-dimensional symphony of the heliosphere, a map that will frame every future anomaly within its proper currents. On Earth, laboratories replicate the sky. In clean rooms gloved in sterile light, scientists suspend metallic dust in electromagnetic traps, simulating the conditions the comet endured. Lasers strike the grains. Cameras watch their slow dance through plasma. Each motion, each spark, translates into equations that may explain how sunlight and magnetism conspired to paint a tale backward. The work is meticulous, repetitive, almost devotional, a ritual of understanding performed grain by grain. And orbiting above them all, the James Webb Space Telescope keeps vigil. Its mirror, cooled to silence, surveys the dark beyond Neptune for faint reflections that might be lingering fragments of the interstellar traveler. Some models suggest that a haze of its dust continues outward, scattering infrared light invisible to human eyes. JWST's instruments trace these whispers, looking for echoes of nickel and carbon dioxide, for any sign that the anti-tails particles still drift through the solar wind, carrying their message toward the void. Every mission that 3i Atlas inspired is part of a larger realization, that astronomy is no longer content merely to observe. It must anticipate. The galaxy's traffic is constant. Earth just happens to lie near a crossing. To miss the next encounter would be to turn away from the cosmos at the very moment it tries to speak. In the quiet corridors of universities, young researchers study the comet's legacy through terabytes of archived data. They scroll through spectral lines, photometric curves, magnetic plots, and see patterns that their predecessors missed. Machine learning models trained on this single anomaly now search through decades of cometary data, finding subtle hints that perhaps occasionally others have shown similar sunward whispers. Faint, overlooked inversions hidden in the noise. The implication is staggering. 3I Atlas may not be the only one to bend its light homeward. As the tools evolve, so does the philosophy behind them. Each new instrument carries a measure of humility. The understanding that technology is not built to dominate the cosmos, but to join its rhythm. When the next visitor comes, whether tomorrow or in a century, our observatories will not simply record it, they will converse with it. Cameras will track in unison, probes will reorient, algorithms will rewrite themselves mid-flight. The frontier of observation will move from reaction to resonance. For now, the work continues quietly. Engineers run stress tests in the silence of midnight labs. Astrophysicists cross-match databases. Plasma specialists wait for solar storms to test their models. The ghost of 3I Atlas hovers in every conversation. A reminder that knowledge begins not with certainty but with wonder. If one looks up on a clear night, beyond the cities and their noise, the sky appears serene. Yet behind that stillness flows the sun's constant exhalation, curling magnetic tides invisible to the eye. Somewhere out there, another wanderer is already on its way, carrying dust older than Earth, moving through those same tides. And when it arrives, it will find us ready, with instruments born from the memory of a comet that pointed the wrong way, and taught us to build tools that chase ghosts across the light. By late October 2025, 3I Atlas was leaving. The last exposures from Hubble showed only a dim blur, its twin tails thinning into the solar haze. What had once commanded the attention of every major telescope was now little more than a whisper in the data. Yet behind that fading point of light lay a new quest, the desire to know where it had come from, and how long it had wandered before arriving at our star. To trace an interstellar object is to perform a kind of celestial archaeology. Astronomers take the arc it carved through the solar system and extend it backward, correcting for the motion of the sun, the planets, and even the slow drift of nearby stars. It is a reconstruction of memory, performed not with fossils but with orbits. When researchers at Gaia and JPL began this work for 3I Atlas, they quickly realized how ancient its journey had been. The velocity, nearly 130,000 miles per hour, was too high to belong to any native body. Its incoming vector pointed not to the ecliptic but far above it, as if the traveler had fallen from the galactic sky. Simulations ran for weeks. The orbit, when projected backward through the galaxy's gravitational field, crossed regions far beyond our local spiral arm. One cluster of solutions converged near the Perseus arm, some 250 light-years away, where dense molecular clouds breed stars in tangled filaments of dust and magnetism. There, in the dying light of a binary system, the story may have begun. Imagine it. A young stellar pair circling too close, their gravitational dance flinging fragments of their birth disk outward. In one catastrophic moment, perhaps the explosion of a companion star or the collapse of a forming planet, a shard was torn free. That shard, laced with nickel, cobalt, and frozen carbon dioxide, drifted into the night. For millions of years, it sailed through interstellar darkness, crossing regions where starlight fades to nothing, where radiation and magnetic fields sculpt matter into silence. Each collision with cosmic dust eroded it. Each passing shockwave altered its surface chemistry. It became what we saw, a relic polished by eternity. By comparing isotopic ratios from its dust spectra with models of stellar evolution, scientists found signatures of heavy elements that could only form near massive, short-lived stars. Its birth, then, was violent, somewhere amid supernovae that enriched its native nebula with metals. The nickel lines that puzzled researchers during its observation were not anomalies. They were memories imprinted by the heat of creation. Its age told another story. Exposure models suggested that the outer layers of 3I Atlas had endured bombardment from cosmic rays for tens of millions of years. Each particle impact recorded time like tree rings, whispering that this wanderer had crossed the gulf between stars longer than human civilization has existed. When it finally slipped into the sun's gravity well, it did so not as a fresh emissary but as an ancient survivor. The process of backtracking such an object is as much philosophy as physics. Every uncertainty, every gravitational nudge unaccounted for, spreads the potential origin wider, until the past becomes a cone of possibility stretching across half the galaxy. Somewhere within that cone lies the home star, now long gone or unrecognizable. Perhaps it still burns, unaware that one of its forgotten fragments once touched another sun. Perhaps it died millennia ago, leaving its dust to drift forever. For planetary scientists, these realizations changed everything. Each interstellar object is a sample return mission conducted by the universe itself. No spacecraft could yet cross the voids between stars, but the stars occasionally send their relics to us. 3I Atlas, with its alien chemistry and reversed tail, became both specimen and scripture. Its dust recorded the physics of another world's infancy. Its motion traced the geography of the galaxy. Through it, humanity glimpsed the network of stellar exchange, the quiet trade of matter that binds suns together into one galactic family. In laboratories on Earth, spectroscopists examined grains collected indirectly through light. Within those patterns, they saw echoes of worlds that might once have orbited the parent star, planets vaporized, disks dispersed, elements repurposed by time. The comet's metallic heart was a message from that vanished system. We were here. Our dust still moves. As 3I Atlas retreated beyond Mars's orbit, the sun behind it grew smaller. A pale sphere reflected faintly on the trailing dust. The antitail, once brilliant, now only a phantom of scattered particles, curved delicately toward the light. Some astronomers noted the irony. Even as it fled, it continued to point home. From its trajectory, JPL projected that it would exit the solar system entirely by 2028, bound again for interstellar space. Beyond the heliopause, solar gravity would loosen its hold, and the comet would resume its long voyage through the dark, perhaps for another 100 million years, until captured or dissolved. By then, the sun's map imprinted on its dust would be just another layer atop the countless others, a record of our small corner of the Milky Way. In a sense, tracing 3I Atlas's origin also traced our own. The metals in its dust, nickel, cobalt, iron, are the same elements that course through human blood. They were forged in similar furnaces, spread by ancient explosions, gathered by gravity into stars and planets, and, one day, into living observers who could watch their fragments return. The comet's journey was not a foreign intrusion, but a reunion. A reminder that all things in the galaxy share a common ancestry and fire. When its final photons reached Earth, they carried both directions at once, outward, into the infinite, and inward into memory. The telescopes powered down, data archived, yet the question lingered: how many others are on their way? The sky above seemed less empty now, populated not by distant, silent points but by paths, threads of motion connecting the sun to the broader weave of the Milky Way. In that realization, humanity stood at the edge of comprehension, gazing into a space no longer indifferent but intimate. Thor's Atlas had come not merely to defy light, but to remind its observers that they too are fragments traveling between stars, momentary dust illuminated by a passing sun. When the light of 3I Atlas finally dimmed below the reach of the most patient telescopes, the silence that followed was not emptiness, but reflection. For months, the comet had demanded action. Measurements, simulations, equations scribbled under artificial suns in windowless labs. Now the work paused, and the deeper reckoning began. In every age of science, there comes a moment when an anomaly rewrites humility. The Sunward Tendril was such a moment. It had not broken any law of nature, only exposed how incomplete our reading of those laws remains. For the men and women who watched it, the realization was almost spiritual, that understanding the cosmos is not a conquest but a dialogue, and that sometimes the universe answers in riddles. Einstein once wrote that the most incomprehensible thing about the universe is that it is comprehensible at all. Atlas seemed to echo this sentiment, but backward. It reminded its observers that comprehension is never final, that every solved equation births another mystery. The anti-tale was a signature written in negative space, a cosmic inversion reminding humanity that truth and paradox are often twins. At NASA's Goddard Space Flight Center, an image still hangs on a wall, a composite of Hubble JWST and solar orbiter data showing the double-tailed figure suspended against the dark. To the physicists who built the models, it represents more than a phenomenon. It is a mirror. One tail aligns with certainty, the other with curiosity, and between them lies the narrow corridor of wonder where discovery lives. For the philosophers of science, the event revived an old question. Why does progress require surprise? Why must knowledge advance through contradiction? The answer hides in the very method of inquiry. Every paradigm in astronomy, heliocentrism, relativity, quantum fields, began as an anomaly, a deviation from expectation that refused to vanish. In that sense, 3I Atlas was not a rupture but continuity, another nudge from the cosmos to look closer. Students who had watched the live data feeds from observatories speak of the experience as formative. It was not the spectacle of the comet's glow that stayed with them, but the collective pause. The sense that for a few nights, everyone on Earth looked up with the same confusion and the same desire to understand. That shared bewilderment became its own kind of enlightenment. In the years to come, papers will classify 3I Atlas within the tidy lexicon of science, a hyperbolic interstellar body exhibiting a persistent sunward dust filament caused by coupled magnetic radiative forces. Yet those who were there will remember it differently. They will remember how it felt, the way data transformed into meaning and meaning into humility. For in the anti-tale's gentle defiance, they glimpsed the fragility of certainty itself. From that fragility grows strength. When models fail, they invite creativity. When instruments contradict expectation, they demand new instruments. Already the inversion has inspired mission proposals and theoretical frameworks that reach beyond comets, toward a deeper understanding of stellar magnetism, cosmic dust, and plasma interactions. It has reminded humanity that failure is fertile ground, that confusion is a compass pointing toward discovery. And beneath the mathematics, a quieter lesson endures. The anti-tale was not rebellion, it was reconciliation. The dust of another world met the light of ours, and for a moment they negotiated. Each yielded a little, each revealed a little, and between them a pattern emerged. That pattern is the essence of science, not dominance but relationship. In classrooms, professors now begin lectures on cometary dynamics with a slide of 3i Atlas and a single sentence beneath it. Remember the inversion. It is shorthand for the humility every discipline must learn, to trust the universe enough to be astonished by it. As the comet's trail continues outward, beyond the orbit of Jupiter, the sun still glints faintly on the last fragments of its dust. Those particles spinning through the solar wind carry within them the imprint of two intelligences, the star that warmed them and the minds that wondered at their behavior. The dialogue continues, written not in words but in light. And so, 3i Atlas joins a lineage of cosmic teachers whose lessons are not in what they explain, but in what they leave unexplained. Every photon it reflected back toward Earth was a question disguised as beauty. In learning to read those questions, humanity took another small step toward wisdom, the kind that knows knowledge is never complete. When historians of science look back on the early 21st century, they may not remember every equation, but they will find, among the archives of images and data, a quiet revelation that in 2025, an interstellar wanderer turned its face toward the sun and, in doing so, turned ours toward the unknown. The comet is gone. Its path now lies beyond the reach of telescopes, a fading line in a map of stars that never truly keeps still. Yet in the silence left behind, its story lingers like the afterglow of a distant flare. In the first days after 3i Atlas slipped from view, the observatories fell quiet. The instruments that had followed it for months turned toward new targets, and the scientists who had chased its every flicker returned to their normal work. But something had changed. For once, the departure of a comet felt less like an ending and more like a beginning, an opening into reflection. The last data showed a final shimmer of dust catching the sun's rays as the object drifted toward interstellar darkness. The two tails, outward and inward, thinned into invisibility, but their geometry endured in the minds of those who had watched. That faint sunward line seemed to whisper a message not in language, but in gesture. Even light, given time and the right kind of matter, can appear to draw the universe inward. In the months that followed, researchers spoke less of equations and more of meanings. What does it mean, they asked, for sunlight to seem to pull? The answer was not purely physical. It was metaphoric, philosophical, human. For centuries, light had been our symbol of certainty, the straight path, the clarifier of shadow. Yet, the anti-tale of 3i Atlas revealed that illumination is not always separation. Sometimes it attracts. Sometimes understanding does not push ignorance away but draws it closer, asking us to see what we had once dismissed as impossible. The reflection rippled beyond science. Artists, poets, and filmmakers turned the event into metaphor. Dust moving backward, light behaving like memory. In museums, renderings of the comet hung beside ancient depictions of mythic travelers. Humanity had found in a stream of plasma the oldest of archetypes, the wanderer returning home. In the quiet offices of researchers, the tone changed too. They began to speak of cooperation, not conquest. The universe, they said, does not yield its secrets to interrogation, but to listening. When light pulled the dust of 3i Atlas inward, it was as if the cosmos itself was modeling that lesson, showing that attraction, not aggression, reveals structure, And in that reflection lay something larger than data: empathy for existence itself. Every comet, every photon, every molecule follows its own necessity. The universe is not chaos but conversation, a continual negotiation between energy and matter, between outward motion and return. The anti-tail was simply the visible trace of that deeper truth, a diagram of reciprocity drawn across millions of kilometers. Philosophers of science began to cite the event as an emblem of the humility turn in modern astrophysics, where, once the cosmos was viewed as a stage for human curiosity, it now appeared as a partner in thought. The inversion of light became a symbol of perspective, a reminder that we too are dust drawn inward by a star, obeying the same forces, part of the same choreography. For the public, the meaning was simpler, but no less profound. Images of three-eyed Atlas spread through social media, a pale arc against blackness, one tail pointing toward the sun. Comments beneath them spoke of hope, of paradox, of longing. People saw in that curve a reflection of themselves, of the strange human urge to move toward what dazzles, even when it burns. The scientists who had spent months buried in numbers felt the same pull. Late at night, long after conferences ended, they would re-watch the time-lapse videos. A pinprick of light elongating into a filament, then dissolving. It was there that the emotion lived, not in discovery, but in disappearance. The knowing that every phenomenon, no matter how luminous, must eventually fade, leaving only understanding in its place. By December, the comet had crossed beyond Jupiter's orbit, its path now nearly invisible except to simulation. Somewhere ahead lay the heliopause, the border where the sun's wind meets the galaxy's breath. When it passes that invisible wall, Three-Eye Atlas will become what it once was again, a wanderer between stars carrying traces of two suns upon its surface. The next civilization it passes, if such exists, will see that faint layer of dust and perhaps wonder what story it tells. Back on Earth, the archives of its journey are complete. Terabytes of images, spectra, magnetic readings, and one unquantifiable thing: wonder. Future generations will study the data, correct the models, rename the mystery, but they will still find the echo of awe within the math. Because awe is data too. It is the part of science that no equation can replace. And so the final voice of the documentary belongs to the silence between orbits. The screen fades to the black of interstellar space. A faint streak of light crosses it, then vanishes. Perhaps the universe speaks in reversals: light that pulls, darkness that reveals, visitors that leave us not with answers, but with mirrors. The music swells, the stars drift, and the camera turns slowly back toward the sun. It gleams, distant yet intimate, its light traveling outward in every direction, and somewhere faintly, one tiny particle of dust still travels inward, completing the circle. In that moment, comprehension and wonder meet, and the story of the Sunward Tendril closes not with certainty but with grace.